Hi everyone! Today I am excited to share with you Project kikipounamu, an enterprise-grade distributed ASR system that tackles one of the most challenging problems in speech recognition, handling massive concurrency without compromising reliability. What started as a typical monolithic ASR service has evolved into a resilient, event-driven microservices architecture that recently survived a stress test with 500 concurrent connections. Let me walk you through how we got here. Let's start with the big picture. My system is built on 3 distinct layers, and the magic happens in how they communicate. At the top, I have my users, whether they're connecting from laptops, mobile devices, or desktop applications, all communicating through WebSocket connections for real-time audio streaming. In the middle, I have my Go gateway layer. Think of this as a fortress. It is designed to handle thousands of concurrent connections simultaneously. Why Go? Because of its incredible concurrency model. Each connection costs only a few kilobytes of memory, allowing me to scale horizontally with ease. At the bottom, I have my Python worker nodes. These are the workhorses doing the heavy lifting running ASR inference models on either GPUs or CPUs, depending on what is available. Now let me tell you a story about a critical problem that forced me to completely rethink my messaging architecture and led to what I consider the most elegant design decision in this entire system. The crisis. ON explosion in my early implementation. I hit a wall. Look at this chaos. Every single user connection opened its own Redis subscription to listen for results. With 500 concurrent users, I had 500 Redis connections. I was literally running out of file handles. The system was grinding to a halt with a classic, too many open files panic. This is what I call the naive subscriber pattern, and it simply doesn't scale. I needed a fundamental rethink. The solution, dual channel philosophy. What emerged from that crisis is this: a dual-channel architecture where I use 2 distinct data pipelines flowing in opposite directions, each optimized for a completely different purpose. On the left, the outbound pipeline, task distribution via Redis Streams. See these thick, solid pipelines with persistent symbols. When the Go gateway receives an audio chunk, it pushes it into the stream. The data is durable, persisted to disk. If Redis crashes and restarts, these tasks are still there. Workers pull from this stream using XRead group. Consumer group semantics guarantee. Each task is processed exactly once. Notice the autoclaim annotation. This is where my zero-loss recovery happens. This channel is designed for reliability. Tasks are critical business data. I cannot afford to lose them. On the right, the inbound pipeline result notification via Redis pubdo. Sub now here is where I solved that ON explosion. See these thin, lightning, fast wireless pipelines with speed lines. When the worker finishes processing, it publishes the result to a pub sub-channel. There is no persistence here. It is fire and forget. If a client has disconnected, the message is simply dropped. But the latency, sub-millisecond. Instant push to WebSocket clients. And here is the critical optimization. Instead of 500 users creating 500 subscriptions, I have one global result subscriber, a single background Go routine in the Go gateway that subscribes to this channel. When a result comes in, it looks up the corresponding WebSocket connection in memory based on the session ID and pushes it directly to that specific client. The impact. I reduced Redis subscription connections from ON complexity, scaling linearly with users to O1, constant regardless of how many users connect. This is just an optimization. It is a fundamental architectural shift that makes true horizontal scaling possible. This channel is designed for performance. Results are ephemeral UI updates. If a user refreshes their browser, I don't need to replay all previous results. The trade-off matrix. Look at this comparison table floating between the pipelines. This is the trade-off matrix. Redis streams, persistence. At least once delivery. Task queue semantics, Redis PUB, sub, ultra, low latency, fire, and forget. Real-time notifications. I am using the right tool for each job. This is what I call separation of concerns at the messaging layer. Streams for reliability, pub bor sub for real. Time performance, maximum system efficiency, without compromising on either dimension. The arrows show the complete life cycle. Tasks flow left to right, through workers, and results flow right to left back to clients. It is a beautiful symmetry, born from solving a real production crisis. Now let's talk about what really matters. Performance under fire. On the 11th of December, I conducted a large-scale stress test. These aren't theoretical numbers. They real measurements from production, equivalent loads, 500 concurrent connections, all established successfully. The gateway didn't crash, didn't leak memory, didn't even break a sweat. 100% gateway uptime. This is the shield icon you see here. Even when my backend workers were completely overwhelmed, and they were with only 22% of requests completing successfully, the gateway layer remained rock solid. Users could still connect, still send audio, still queue tasks. The system degraded gracefully instead of falling over. CPU usage below 10%. Look at this thermometer. I am barely touching my compute capacity at the gateway level. This is the power of Go's concurrency model. While Python struggles with a GIL, Go is efficiently multiplexing thousands of connections across available CPU cores. Redis throughput 50,000 operations per second. The message bus is not my bottleneck. I've got headroom to scale much further. Now, you might ask about that 22% success rate at 500 concurrency. That is actually a feature, not a bug. It is a capacity planning reality. When you have limited compute resources, limited workers, queue times increase linearly with concurrency. The architecture is sound. I just need more worker nodes. And that is exactly the kind of problem I want. A problem I can solve by throwing more hardware at it, rather than rewriting code. Concurrency is one thing, but what about reliability? What happens when things go wrong? Look at this workflow. Tasks enter my Redis stream queue from the left. Multiple worker nodes consume these tasks, some running on GPUs, others on CPUs. But notice these workers marked with an X. They've crashed. Maybe they ran out of memory. Maybe the GPU driver failed. In production, failures are inevitable. In a traditional architecture, those tasks would be lost. But I've implemented something powerful. Autoclaim. Watch this recovery arrow. When a worker crashes, its pending tasks don't disappear. Redis Streams tracks them. After a timeout period, healthy workers automatically claim these orphan tasks and process them. It is like a safety net underneath the entire system. This gives me at least on delivery. Guarantees no task is ever lost. This is crucial for enterprise applications, where every audio chunk matters, whether it is medical transcription, legal proceedings, or customer service recordings. The beauty of this approach, it is self-healing. I don't need external monitoring to detect failures and restart tasks. The system handles it automatically at the protocol level. Finally, let me show you the future I'm building, what I call inclusive distributed computing. Look at this visualization. At the center, I have my Redis Streams hub, the central nexus that coordinates everything. But radiating outward, look at the diversity of devices connecting to it. Top left, an old Dell laptop from 2015, CPU gen only, maybe gathering dust in someone's closet. In my system, it is a legitimate worker node, contributing CPU cycles to transcription tasks. Top right, a consumer gaming desktop with an RTX 3060. The owner plays games at night, but during the day, it is processing audio with GPU acceleration. Bottom left, a Mac Studio with a new AMSA chip and unified memory architecture. Apple Silicon is incredibly efficient for certain workloads, and I'm bringing it into the fold. Bottom right, an enterprise server rack with multiple NVIDIA, Alinin cards, the traditional AI infrastructure. But wait, there is more. See these smaller nodes, a Raspberry Pi cluster for edge computing. Even a PlayStation Wu, marked as experimental. But hey, it has got a powerful GPU, a Surface laptop running hybrid workloads. This is heterogeneous distributed computing. Every device is different architectures, different compute capabilities, different locations. But they all speak the same language. Red group, from Redis Streams. Notice the dynamic elements. One device is joining with adjoining. Animation. Another is leaving, but its tasks are being auto-claimed by healthy workers. This system is self-organizing. The requirements Python 3.10 or later, and network access to Redis. That is it. No complex orchestration, no rigid infrastructure requirements. This is what modern distributed systems should look like, bringing your own device from ease and waste to AI powerhouse. Every CPU cycle counts. I'm democratizing AI infrastructure.